So we have an electromagnetic wave. First of all, that's moving in the direction of an increasing z, propagating down the transmission line. It manifests itself in terms of a voltage and current that we call V plus and I plus. Then simultaneously we have another wave propagating the opposite direction, the direction of decreasing z. It too manifests itself in terms of voltage and current, a V minus and I minus. Now, these two propagating waves would seem to be independent. There was nothing that would constrain one wave to the other, at least right now. And so we would have no reason to expect that V plus and V minus would be related to each other. We could somehow say something about one if we knew information about the other. The same thing for I plus and I minus. Again, they are creations of two fundamentally different manifestations, one wave in one direction and a completely different wave propagating in the other. But let's think about the relationship now between plus voltage and plus voltage rather, and plus current. The plus voltage and plus current are the results of the same electromagnetic phenomenon, one single propagating wave. They are children of the same parents, essentially, the electric field and the magnetic field. And so it is reasonable to expect that perhaps there is a more fundamental relationship between V plus and I plus. And of course, really, when you look at it, both of them have the same solution, e to the minus j beta z. They both change the same way with respect to position. The only difference that we see in the results are the complex wave amplitude V0 plus and the complex wave amplitude I0 plus. And so we might ask this question: is V0 plus, that complex wave amplitude, related to I0 plus in any way? Again, it might be reasonable to assume this is true, since they are in fact creations, manifestations of the same single propagating electromagnetic wave. So to see if there's a relationship, let's consult telegrapher equations. We know, of course, the solution to telegrapher equations now. We've determined that from the transmission line wave equations. But let's go back and take those solutions and see what the wave equations or the telegrapher equations might tell us in regard to the relationship between the plus wave voltage and the plus wave current. So from the first telegrapher equations, if we consider only the plus wave voltage, and we can think of this as simply the total voltage where the minus wave voltage is equal to 0, we see that they must satisfy this telegrapher equations. And clearly here we're assuming the lossless approximation where R is equal to 0. Well, in this case, it says the first derivative, or the derivative of the plus wave voltage with respect to position z. Since we know what that plus wave voltage is, we have that from our telegrapher equation solutions, we can go ahead and take this first derivative. So we take the first derivative, or a plus wave voltage function, V0 plus times e to the minus j beta z. Pull the constant out front, take the derivative of the exponential, and we just have minus j beta times V0 plus complex wave amplitude, and then of course the same exponential. If we look at this closely, we see these last two terms are just the plus wave voltage function. V0 plus times e to the minus j beta z is the plus voltage function there. So we take the derivative of the plus voltage function and we get simply the plus voltage function itself times minus jb, hence the result of taking derivatives with an exponential. All right, so what do we do with this? Let's take this result and put it back here. And we're going to rewrite this telegrapher equation, since we've taken our derivative, as this. Notice on the left side we have the plus wave voltage, and on the right side we have the plus wave current. And so we do a little algebra and we can find the ratio now of the plus wave voltage to the plus wave voltage to the plus wave current. So the ratio involves the value of beta, and remember that beta is equal to omega times the square root of LC. Take the product of the inductance and capacitance per unit length and take the square root and multiply by omega. You have beta, or more specifically beta squared would be omega squared times LC. Let's take this result and insert it back into this ratio that we found on the previous page, insert this where beta is, and then do a little algebra, and we find out that that ratio on the previous page can be written as the square root of L over C. And we see a nice symmetry here. Here in beta we have the square root of the product of L and C. Here we have the square root of the ratio of L and C. And this ratio, square root of the ratio of L and C, is then equal to the ratio of the plus wave voltage to the plus wave current. And we look at this, in some ways this is really surprising, almost stunning in the result. And let's see if we can figure out why. So we're taking the ratio of V plus, the V plus function, to the I plus function. Of course, each of these functions are complex functions of position Z. And we just showed that if I take the ratio of a complex function of position Z and another complex function of position Z, the result is a constant with respect to position Z. The square root of L over C does not depend on the position. In other words, the ratio of these two things is independent of location. Now, since each of these two terms were dependent on the same function with respect to Z, e to the minus j beta Z, it's probably not a surprise that the ratio will be independent of Z, since those two functions cancel out. There's another interesting result, though, and this causes great confusion for students, is that the ratio of these two complex functions, and generally speaking, they'll have both a real and imaginary part, the ratio of these two complex functions is a real valued constant, the square root of L over C. The other constants, the complex wave amplitudes, V0 plus, for example, they're constant with respect to Z, of course, but they are complex. They have both real and imaginary parts, generally speaking. Yet the ratio of the two, it turns out, will have the real value, square root of L over C. We'll talk more about that in a second. So we can see, mathematically speaking, that the plus wave voltage function and the plus wave current function are very directly and simply related. If we know one of the two functions, we can determine the other function immediately if we know the square root of L over C. And so one way to write this is that we can write the voltage now for the plus wave voltage function as simply the current function times the square root of L over C. Of course, we could also write then the current function as the voltage function divided by the square root of L over C. So there's a simple relationship, and again, we alluded to this earlier. It's really no surprise, since the plus wave voltage and plus wave current are manifestations of the single electromagnetic wave propagating down the transmission line. Again, what we don't find is that there's a direct relationship between, let's say, V plus and V minus. Those two functions, V plus and V minus, are manifestations of completely different, two different electromagnetic waves. Later on, we might do something that constrains them, but generally speaking, right now, they could be any two functions. But V plus and I plus are related by this simple value, this simple real value, the square root of L over C. All right, so what about the minus wave, the electromagnetic wave that propagates in the direction of decreasing Z? It creates a voltage and current that we call V minus and I minus, and we have functions for them with respect to position Z. How are they related? Well, we could do the same procedure as before, where we take the result, insert it into the telegrapher equation, take the first derivative, and then do a little algebra, and we would come up with this result here. From this result, if we take the ratio of each side and insert the value for beta in terms of the square root of LC, we can conclude that the ratio of the minus wave voltage to the minus wave current is equal to minus the square root of LC. So we could write that the minus wave voltage is equal to the minus wave current times the square root of LC minus the square root of LC. So these are the same results as we got for the plus wave. The only difference is this sort of annoying minus sign. And one of the questions is why do we have the minus sign there? Well, without belaboring the mathematics too much, essentially the reason we have a minus sign harkens back to our original notation with respect to current. Remember, our total current, the sum of I plus and I minus, we defined as positive when flowing from left to right in the direction of increasing z. And so we use that same notation, that same definition for I plus and I minus. But there's a problem here in that the plus going electromagnetic wave, it's propagating in the direction of increasing z, and so it's propagating in the direction of positive current. But for the minus going wave, it's moving in this direction from right to left. It's propagating in the direction of decreasing z, and so it's propagating in a direction that's opposite of our notation, of our current notation here. And effectively, that's why the minus sign comes about. If we wrote the positive current for the minus current as positive when flowing in the direction of decreasing z, the same as the direction of propagation, we would end up with a result where both ratios would be equal to the square root of L over C. Now, I prefer that result in that notation. In another course, 723, when I do this, I write this current in the arrow. I define it as positive in the opposite direction. That will change our telegrapher equation slightly, because from KCL then, the total current is not the sum of I plus and I minus. By KCL, the total current would be the difference between I plus and I minus if I've defined positive current in the opposite direction. You know, KCL, if they're going the opposite direction, you take the difference between the two to find the resulting total there. But that is not standard to write it in the opposite direction. And so I do that in 723, but I don't do it in this class to try to come up with results that are consistent with most textbooks. Again, the annoying thing is we end up with that minus sign for the ratio of V minus to I minus. Now remember, a minus sign is, multiplying by minus 1/2. We're talking about complex numbers here, so that really is a phase shift of 180 degrees, a phase shift of pi radians. You take a sinusoid and you multiply by -1. It's the same thing as if you shifted it by pi radians. So the ratio of plus wave voltage function to plus wave current function is equal to the square root of L over C. Likewise, the ratio of V minus to I minus is minus the square root of L over C. Regardless, in either case, the square root of L over C shows up an awful lot in both of those solutions. It shows up so much that we are going to give it a specific value. We're going to call the square root of L over C the value of Z0, the characteristic impedance of the transmission line. Now, I've written here that this characteristic impedance Z sub 0, and I don't really like this notation for a couple of reasons. One is we have too many Z's in microwave engineering. I'd rather give it another value besides Z. The subscript 0 is sort of harkens students to remind them of things like V0 plus and V0 minus. And of course, that subscript means the value at Z is equal to 0. This characteristic impedance isn't a value of any impedance anywhere. So the subscript subscript 0 does not imply that we're evaluating something that the index Z is equal to 0. So that can cause confusion as well. I write it as a function of omega, and generally speaking it is, but if we apply the lossless transmission, what we find, and we just showed, is that the ratio of plus voltage to plus current, for example, is independent of frequency omega, simply the square root of L over C. So for the case of a lossless transmission line using the lossless approximation, this characteristic impedance is independent of omega. It's a constant, and one of the few things that is constant with respect or independent with respect to omega. So the characteristic impedance of a transmission line depends only on the transmission line parameters L, inductance, and capacitance C. And this is very important. The characteristic impedance depends on these two things, L and C. And those characteristics are immutable. We can't change them. Whether I have a transmission line that's in a circuit, or I take the transmission line and stick it in my pocket or throw it in the trash, it still has the same inductance and capacitance per unit length, and therefore its characteristic impedance is the same, regardless of what circuit I put it in, what what I connect to either end of it. The characteristic impedance is the characteristic impedance. It's just like a 15 ohm, 15k ohm resistor, let's say. A 15k ohm resistor is a 15k ohm resistor. Its resistance is 15 kiloohms. If I took that 15k ohm resistor and I stuck it in one circuit and put 10 volts across it, it's still 15k. If I put it in a different circuit where I had minus 3 volts across it, it's still 15k. If I took that resistor and took it out of a circuit and stuck it in my pocket, it would still have a resistance of 15k. This characteristic impedance of a transmission line is a device parameter independent of where you put it or what you connect it to. And that's very important that you understand. It depends on inductance and capacitance per unit length only. All right. So a lot of times students will say, well, in this circuit, the characteristic impedance is this, but if I change this thing now, it's a different value. No, it is what it is. It is a characteristic, a parameter, immutable of a transmission line. It is unaffected by the things attached to the end. So it's a very important point to make sure that you understand. All right, there's some other things that are very important to note about characteristic impedance of our transmission line. First of all, it has units of impedance. That's why we call it characteristic impedance. In other words, units of ohms. Now, it may not be evident to you that the square root of L over C would have units of ohms, but remember the square root of L over C is equal to V plus divided by I plus. And of course, the ratio of the plus wave voltage to the plus wave current must have units of ohms by Ohm's law. So you can show that this, in fact, does have units of ohms, but again, we can infer that by simply looking at the previous equation relating V plus and I plus. It is a purely real value, the square root of L over C. L and C are real values, so the square root of L over C are real value. Now, again, this is true only if we have, to the extent that we have a lossless transmission line. Again, we're applying the lossless approximation here, where effectively we're saying the resistance and conductance R and G are equal to 0. Again, they're not really equal to 0, but they're so small that we are mathematically setting them to 0. And of course, that simplifies our mathematics. One of the things it does is make the characteristic impedance purely real. In a real transmission line, we had a little bit of loss, we would find there'd be a tiny imaginary part. So it's so small, essentially, we neglect it and refer to this as a real value. Finally, we find for the lossless transmission line again that the characteristic impedance is independent of frequency omega. Now, here's the problem that we run into with students when you look at this. Gee, a device that has units of ohms is purely real, or let's say, I shouldn't say device, let's say an impedance, characteristic impedance. An impedance with units of ohms, it's purely real, and it's independent of frequency. Gosh, that sounds exactly like a resistor. A resistor has units of ohms. Its device parameter or is units of ohms. Of course, resistor, that resistance or impedance is purely real. And of course, the impedance of a resistor is independent of omega. So it sounds awful like our transmission line in some way is a resistor. And oftentimes students will try to conclude this and model this or mathematically analyze it in a way as if it were a resistor. But is it a resistor? Well, clearly, no, it is not. All right. And this is very important that you understand. All right. Lots of exclamation points here because this is, again, a mistake that students make that leads us to great confusion and poor scores on exams. Remember, the characteristic impedance, the Z0 square root of L over C, inductance and capacitance. This is a characteristic of a lossless transmission line, a big two-port hunk of reactance, and reactance only. It is the least resistive looking thing that we'll analyze there. There is no R and there is no G. So to reiterate, in our lossless approximation, the resistance and per unit length, the conductance per unit length is equal to 0. We're assuming our wires are perfectly conducting and the dielectrics separating our wires are perfect insulators. And so we can't absorb any energy at all. Instead, we just have inductance and capacitance per unit length, a big hunk two-port hunk of reactance. And so it is incorrect to infer that a transmission line somehow has a resistance associated with it, even though the characteristic impedance of a transmission line will be a purely real frequency independent value that is specified in ohms. One of the common characteristic impedance for transmission lines is 50 ohms. We have a 50 ohm line. What does that mean? Again, students in a lot of practicing engineers will hear the value of 50 ohms and they'll assume that has something to do with a resistance somewhere. Somewhere in this thing there's a 50 ohm resistor, but again, there is no resistors anywhere in a lossless transmission line, just inductors and capacitors. So since we started talking about transmission line analysis, we began with, in a lossless line, the parameters of inductance per unit length and capacitance per unit length. But since then, in our mathematical analysis, we've discovered a value which we call beta, which is omega times the square root of the product L and C, and then another value Z0, characteristic impedance, which is equal to the square root of the ratio of L and C. These two values, beta and Z0, are the two values that we use to characterize a lossless transmission line. These are the two most fundamental parameters of a transmission line. Now, you say, do we add these to our previous fundamental parameters of a lossless line of L and C? No, we don't now have four parameters. Essentially, we've transformed our original two real values, parameters of L and C, into a new pair. We've just done a transformation of that into beta and Z0. And we see that both beta and Z0 are dependent on L over C. Again, in a nice symmetric way. One is the square root of the product of L and C. The other is the square root of the ratio L and C. If we look closer, we can do a little algebra and find that there's an interesting relationship. If we take the product of beta and Z0, we get omega L. And omega L, of course, is the magnitude of the series impedance that we get for a transmission line. Since it's lossless, our series impedance is purely reactive, J omega L. The ratio of beta to Z0 rather, gives us the value of omega C, which is our shunt admittance that we get for our transmission line. Again, G is equal to 0 here, so the shunt admittance would be J omega C. This gives us the magnitude of that. And so there's a nice symmetry between L and C, beta and Z0, and series impedance and shunt admittance of our transmission line. One last thing, notice beta does depend on omega, but Z0 does not. And again, this is for a lossless line when R and G are equal to 0. So one of the problems that students have with characteristic impedance is trying to make sense of this value. What does it tell us? We have a transmission line. We say its characteristic impedance is 50 ohms. What does that mean? Sometimes students will think, well, that means the input impedance is 50 ohms. But remember, a two-port device, like a transmission line, doesn't have an input impedance. Only one-port devices have input impedance. If we connect something to the end of our transmission line, then we've created a one-port device, and it will have an input impedance. And that input impedance, to be sure, will be dependent on the characteristic impedance Z0, but generally speaking, it will not be equal to Z0. Not at all. It could be very, very different from Z0. So does Z0 say something about the transimpedance parameter? Two-port device, all right, doesn't have an input impedance, but it does have four transimpedance parameters in impedance matrix. Well, clearly Z0 can't be one of those transimpedance parameters either, because a lossless transmission line, of course, must have transimpedance parameters that are purely imaginary, no real component at all. Z0 is purely real. And so even though we'll find later that the transimpedance parameters of a length of transmission line, lossless transmission line, will depend on the characteristic impedance Z0, it will not be equal to Z0. Again, Z0 is just a characteristic of the transmission line. It shows up in all of our math and all of our analysis when we do transmission line mathematics or analysis, but it's not something that we can point to directly and say, oh, it's this impedance here or it's that impedance there. It is a value, a characteristic of the transmission line. And what characteristic are we trying to express with the characteristic impedance? Well, really what Z0 does is this. If we take our transmission line and we propagate a single wave down that transmission transmission line. Either way, it will produce a voltage and a current simultaneously, V plus and I plus, or if it was going the other way, V minus and I minus. And the question is, in what ratio does it create voltage and current? If I have an electromagnetic wave of a certain power, and I propagate it down the line, does it create more voltage and less current than some other transmission line, or does it create more current but less voltage than a different transmission line with the same propagating wave and the same power? What is the characteristic of the transmission line in that? How does it manifest itself? More current or more voltage as the wave propagates down the line? Well, that's what the characteristic impedance tells us. If we go through and we find that the characteristic impedance of a transmission line is very high, all it really tells us is that for a single propagating wave, the voltage manifested for that wave, this is not the total voltage, just the voltage of the one propagating wave. If Z0 is big, it means that V plus is pretty big and I plus is pretty small. It tends to manifest itself more in voltage and less in current if the characteristic impedance of the transmission line is larger. Conversely, therefore, if Z0 is smaller, numerically smaller than other transmission lines, wow, that's a pretty darn small characteristic impedance for that transmission line. What does that tell us? It means that if I propagate a wave down that line of a certain power, it will manifest itself more in terms of current and less in terms of voltage. It just says, for a single wave, what is the relationship between the voltage and current that it creates. And that's all it says. That's the only thing it says. It's a very important characterization, the characteristic impedance. And of course, this fact will have great ramifications when we start doing analysis of transmission lines in real circuits. But we really can never go through and specify Z0 is equal to some specific circuit element or value that we're used to in during circuit analysis. Now, to be sure, there are times when some of our values will be equal to Z0. Sometimes we'll find that we connect something to a transmission line and an input impedance happens to be equal to Z0, and I use the term numerically equal to Z0, or I try to differentiate the fact that it is numerically equal to the same value Z0 from some idea that it is physically a definition of Z0. We could have transimpedance parameters perhaps that have Z0, in fact will have Z0 in their results. But again, think back to what the characteristic impedance actually tells us about the transmission line. It just says how a single wave propagating the line will manifest itself more or less in terms of voltage or more or less in terms of current. All right, since we know that characteristic impedance Z0 is the ratio of the plus voltage function to the plus current function, if we were to evaluate that, the e to the minus beta z exponentials in the numerator and denominator cancel out, and we'll see that they are likely, characteristic impedance is likewise equal to the ratio of V0 plus to I0 plus. And of course that makes sense. I0 plus is the plus wave current evaluated at Z is equal to 0. It's one point in the line. And likewise V0 plus is the voltage at Z is equal to 0. If the ratio of the plus voltage to the plus current is Z0 at every point in the line, then certainly it is at the specific location where Z is equal to 0. And so we can say V0 plus divided by I0 plus is equal to Z0, or we can rearrange it in this form here where we say I0 plus is V0 plus divided by Z0. For the minus going wave, we do a similar thing here, relate the complex wave amplitude I0 minus to the complex wave amplitude V0 minus. And notice there's a minus sign there in that relationship. So why are we pointing this out? Remember, in the telegrapher equation solutions, we said there are 4 complex constants that we had to find. V0 plus, V0 minus, I0 plus, and I0 minus. We found that 4, we found everything. But we just found that really it's not 4 complex values, it's 2 pairs of complex values, V plus and I plus, that are related simply by the characteristic impedance of a lossless transmission line. Another pair is I0 minus and V0 minus, again, related simply by the characteristic impedance of the transmission line. If I know I0 minus, I immediately know V0 minus if I know the characteristic impedance. Likewise for V0 plus or I0 plus. And so the quest that we have in terms of transmission line circuit analysis really has been reduced from trying to find 4 different complex numbers to really just finding 2 complex numbers, 2 complex wave amplitudes. Generally speaking, V0 plus and V0 minus, although we could also use I0 plus and I0 minus. The important thing is we need to find 1 plus complex wave amplitude and 1 minus complex wave amplitude, because once we find 1 positive complex wave amplitude, we can immediately determine the other. Likewise for the minus complex wave amplitudes. All right, we're going to codify all this by inserting it back into our telegrapher equation solutions. Remember, our original telegrapher equation solutions had 4 complex wave amplitudes. From these relationships, we're going to rewrite them in terms of simply 2 complex wave amplitudes. And those 2 complex wave amplitudes are V0 plus and V0 minus. Now, for total voltage, we don't really change anything. We've already written those in terms of V0 plus and V0 minus only. All right, so this is solution. And of course, we recognize the first term as our plus wave function with respect to position, and this is our minus voltage, the minus wave voltage as a respect to position. So this doesn't change. What changes is when we insert these 2 results into our current results. Instead of having I0 plus here, now we've written it as V0 plus divided by Z0. Instead of having I0 minus here, we now have a minus V0 minus divided by Z0. Again, don't forget that minus sign right there. Before we had a plus, now it's turned into a minus. And of course, then we can write that in terms of the plus wave voltage. All right, again, this is in terms of the wave amplitudes, a constant with respect to position. These are in terms of the wave voltage functions with respect to position Z. Again, it's the same thing, just using the definition of V plus here to write it in this form. And so this is generally how we write the solution to the telegrapher equations. And again, I like writing it in this way, so you'll have to remember exactly the relationship here of V plus, V0 plus times E to the minus J beta Z is equal to this function. Don't forget the minus sign that is here. So now we've gone through and we've converted our telegrapher equation solutions into solutions that depend on only 2 unknown complex values, V0 plus and V0 minus. Those are the 2 values that we need to find. Once we find them, we can find our voltage and current everywhere on the transmission line. So just for completeness, I just want to point out that we could write our telegrapher equation solutions, the total voltage and total current, instead of in terms of I0 plus and I0 minus. So we could use the current wave amplitudes, complex wave amplitudes. They're just as important and valid as the voltage complex wave amplitudes. But generally speaking, we don't. The tradition is to write everything in terms of V0 plus and V0 minus. But I just want to point out there's nothing that's particularly more right to express everything in terms of voltage as opposed to current. We can also do it with respect to current. Again, in this case, you have a minus sign that shows up in the total voltage that shows up here. So don't forget this. This minus sign here, and on the previous page, the minus sign that shows up in the expression for current is very important, because if we didn't have this minus sign, if this were a plus sign, what we'd find is that the ratio of the total voltage to the total current would be equal to Z0. I get this an awful lot. Students are always telling me that the voltage divided by the current is equal to the characteristic impedance Z0. And that is not the case. You can look at these results here. Take the ratio of this voltage and that current. All right, do some algebra, and you'll find you cannot show that it's equal to Z0. And the reason, because it's not equal to Z0. Again, you change that minus sign to a plus, then it turns out it is, but that is not physically correct. That minus sign is the correct physical description of what goes on. The same thing on the previous page. If we looked at the voltage and current written in terms of V0 plus and V0 minus, if we don't have that minus sign there, we'd have a situation where the ratio of those two would be equal to characteristic impedance Z0. But that minus sign is there, and it must be there. It is the correct physical and mathematical description of what goes on. And that tells us then that the ratio of voltage, the total voltage, the sum of the plus wave voltage and the minus wave voltage, and the total current, the sum of the plus wave current and the minus wave current, the ratio of those two, that voltage to current, is not equal to characteristic impedance Z0. So that is sort of the third thing that I get a lot with respect to characteristic impedance. It must be the input impedance. Well, again, a two-port device doesn't have an input impedance. It must be one of the transimpedance parameters. Well, it's a lossless two-port device. The transimpedance parameters have to be purely imaginary. Oh, it's the ratio of the voltage, the total voltage to the total current. No, it's not. It's the ratio of the plus wave voltage to the plus wave current, and essentially the ratio of the minus wave voltage to the minus wave current, but it is not the ratio equal to the ratio of the total voltage to the total current. It is not. And that's a very common mistake that students make, and so make sure you do not make it.